bounce. And when the water bounced off the paddle wheel, more oomph. And he made more money on this than most of the gold miners did on their claims, simply using the laws of physics. You'll apply more impulse to that spinning wheel by bouncing the water than just simply catching it or stopping it. Ain't that neat? Any questions to this time? Okay. Here we have a little device called an air cart. And right now there's a lot of friction with these things. See, they kind of slow down very quickly. A body at rest doesn't remain at rest very long. I mean, a body in motion doesn't remain in motion because I've got an opposing force. And the force of friction, of course, is slowing these things down. What I'm going to do, though, is this is like a vacuum cleaner in reverse. I'm going to throw on the switch, and it's going to blow air jets. Air is going to cut them. You can't see that, but there's a whole lot of little holes there. And air is going to blow out. And these things are going to ride on a cushion of air. And it's pretty nearly friction-free. Let me show you what I mean. Riding almost friction-free. Now let's see what happens here. Watch this. How come it moved? Let's try it again. And how come this stopped? This is common sense. But let's look at it with some care, and we might see more than we would see otherwise. Here's A coming in, and it hits B. When it hits B, what did we see? We saw this one stop and this one continue. And I asked, why did this one start to move? And you would say it started to move because it was belted, right? This one came in, A came in, bam, and belted it, and that's why it moved. When I say belted, more specifically, what happened? There was an impulse on this. Right now, its momentum is 0. This came in and hit it, and an impulse was applied to this. Let's look at only object B, only this one. And we'll focus all our attention on that. I'm going to put a dotted line around only object B. And I can answer the question why object B started to move. Because, bam, there was a force of impact of A on B. And that made B move. And so you guys saw B takes off. So it's easy to see why B started moving. Okay? An impulse acted on it. Its momentum changed. But did you notice also that the momentum of this changed? Let me show you again. Why did this one, why did object A slow down to a dead stop? What slowed this down? To say it slowed down is to say there was a change in momentum. True or false? And if there's a change in momentum, there has to be, true or false, an impulse. And did you see an impulse act on this?
Yes.
Yes, you did. Because if we look at this again. Okay, they hit. If we're only interested in A, we let object A be our system. Is there any force, any impulse acting on A when they collide? Yes. And what's the force that acts on A? B's hitting it. All right? So see that arrow? Wham! So that's what stops A. Let's suppose we focus on both together. Momentum. Momentum. How big was the momentum of this compared to the momentum of this after collision? Did you see that? If we look at both, if we let our system, our concern be both, this acts on this acts on this, how much force is acting on our system? None. See? If our system is only B, then there's a force poking in there. There's a force acting on it, which provides an impulse, and boom, away it goes, B, huh? And over here, if we let our system be A, we can see there's a force from the outside that acts on it. The force of B pokes in and stops it. Now let's concern our system to be both together. Then this acts on this acts on this. The action and reaction are within the system. There's nothing poking from the outside. Let me ask you a question. For this being my system, what's the net force acting on it? Zero. What's the net impulse acting on it? Not so many people said the same thing. You guys see the net force acting on a system is zero. What's the net impulse then? This is the net force multiplied by the time. It's still going to be zero. So what's the change in my momentum if there's a zero impulse? Zero. And the momentum of my system doesn't change. This one stops and this one continues. This one continues with the same momentum this one had. Let's suppose the beginning one, let's suppose this had 5 units of momentum. Boom. Comes to a halt. How much momentum does this move with? So what's the momentum before and after the collision? 5 fives. No change. Which turns out to be a very, very neat idea. And the idea is this. If there's no net force acting on your system, and when you say system, what do you mean by a system, gang? See, I've got 3 systems here. But if I have a system such that the net force is 0, then the impulse is 0. That means the change in momentum is 0. Careful. It doesn't mean the momentum is 0. It means the change is 0. So whatever momentum you have before something interesting happens, you'll have the same momentum after. That's a very powerful idea, and it underlies a lot of physics. Take a spinning system. It's got momentum. Let the system blow up, do whatever you want. I don't care what it does. Check that momentum afterwards, and guess what you got? The same momentum. When you study astronomy, that will be a pillar from which you will build many other ideas. That the momentum that a system has, if you don't mess with it from the outside, whatever momentum it has, it's going to stay. It can't change unless there's an outside force. Outside force means outside impulse. You know that you're sitting in your car, and the car battery is dead, and you got to get out and push the car, but it's raining. So you say, well, I think I'll just sit here and push on the dashboard. You push. Does the momentum of the car change? So you push harder on the dashboard. What are you doing? You're pushing on the dashboard pushing back on you. What's the net force acting on the car? 0. So what's the change in momentum of the car? 0. See, that's why you got to get outside. You get outside, now you push. You push on the ground push on you. You push against the car, there's a force pushing on the car changes its momentum. You got to have an outside force. In the absence of an outside force, what's the change in the momentum of any system? 0. No change. It will simply transfer from one to another. I can show you that with another case of a collision. This time, I'm going to have my colliding cars are going to stick to one another. Okay? And so let's see what we got now. I'm going to move this car with momentum. It's going to hit here. Let's suppose 10 units of momentum. 10. It's twice as massive. One more time. From what you know about physics, I moved body A in with 10 units of momentum. That means its mass times its speed multiplied together to be 10. 10 units, 10 whatever, okay? It hit. Boom. Afterwards, you saw both of them moving. How much momentum for both? 5. Some people say 5. Where'd the other 5 momentum go? Let me say this, gang. Here's your system right here. When these things hit, was there an outside force acting on the system? Was there? No. So is there a change in the momentum of the system? No. So if this got 10 and this got 0, add them together, what do you got? 10. After collision, what do you got? 10. You got the same momentum before and after. Now here's the question you were asking back there. The speed. If the momentum is 10 before and after, okay, what's the speed?
We can assume that they have the same mass.
In this case, they have the same mass. You've got one car coming in with a speed. Let's suppose the mass is 1 kilogram. So it's coming in at 10 meters per second. Let's just make that up. Okay? And it has a mass of 1 kilogram. So what's the momentum of the object? It's 1 times 10 is 10. 10 units of momentum. Okay? Now it hits another car. But this time, instead of bouncing, both cars move together. What's the momentum before and after collision? SS. Same thing. So what's the momentum after collision? But now I'm going to ask, what's the speed after collision? See why some people get mixed up? They get speed, momentum, mass. Oh, there's all these ideas. I can't handle them. I'm going to drop the course. No, 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 no. Get some tutoring. Okay? You see the different ideas. So if you have twice as much mass moving with the same momentum, they must be moving with how much speed? Oh, not 10. Because now this is 1, this is 1. I got, look at this. To begin with, the momentum before is going to be equal to after. Before, I've got mass of 1 times 10, mv, plus, if this was a 0 at the beginning, remember it was 0? Boom, they hit. And then after they hit, I've got how much mass moving? 2. 2. Both cars are moving. So 2 times, and here's what I got to figure out. 1 times 10 is 10, equals 2 times. There are people what can calculate what this must be. Is there anyone in here who can't? Stand up. I want to see what you look like. What's this number here, gang? 5. And so we see, yeah, the 2 cars do move at half the speed. So they'll have the same momentum. I used to live out in Colorado, and I lived near a place where the railroad cars would get together. And it'd have like a lot of mining out there. It'd have sometimes like 80 freight cars going to be pulled to Gunnison, or maybe pulled to Pueblo or somewhere like that. And boy, it used to be tough at nighttime, because at nighttime, these cars would all clank together, like the freight car would come up and they want to get them all clanked together. And it turns out that the coupling between the cars was loose. So instead of them coming up and boom, one great big clank, there'd be clank, and then clank, 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 78, 79, 80, okay, 80 clanks. And whew, now I can go to sleep. But then what happened is they just connected together. Now they're going to pull this way. And what happens is clank, 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 78, 79, 80. And I used to think to myself, why don't they take those couplings and tighten them up so they don't all clank? Why did they do that? Ooh, I know why, I know why, I know why. It begins with F. Physics. Hey, all right. It's because of the physics. Let me ask you guys a question. You want to set into motion 80 freight cars? 80? Let's suppose you tie them all together so there's no loose coupling. So when you start to pull, you pull all 80 at once. Fat chance. You know what's going to happen with that locomotive? Those wheels are going to spin. You ain't going to pull 80 cars. No way. You can't get that much force on your track. You can't do it. But you can do this. You can pull 1. And once you got 1 going, then you can pull another one. And now you got 2 going. Now you can pull another one, and then another, and another. And you can get all those 80 cars moving by pulling them how? Stretch out the what? Begin with T, end with I'm. By stretching out the time, you'll have enough force of friction between that big wheel and that track to get all those cars in motion. That's right. Ain't that neat? It's like taking your courses in school. Do you ever take 80 units at once? Honey, you can't pull 80 units at once, right? It's like taking a summer course and maybe like 3 calculus courses in the chemistry lab and in 10 weeks. You can't do that. You need more time. You like to see something neat? It's called a swinging wonder. Watch this, gang. I'm going to be lifting one of these balls up. That's strange. Only one ball came out the other side. I'm going to be lifting 2 balls up. That's strange. 2 came out the other side. I'm going to be lifting 4 balls up. No, I lifted 3, I said 4. I thought maybe it might be what I'm saying, okay? And it turns out it wasn't what I was saying. Let's see what happens if I do lift 4 balls up. But there's only 1, 2, 3, 4, 5, 6, 7. Let's try it. That would be wild if 4 balls came out the other side now. If that were the case, it would seem that there must be some underlying rules applied here, huh? Let's try 4. Oh, and we got 4. Let's try 5. Wow! Let's try 6. Woo! Let's try 7. Okay, yeah, ain't that neat? I wonder if there's a reason for that. I wonder if there's a reason. Let me ask you a question. When one comes in, boom, it's got a certain momentum, right? That momentum transfers, and what comes out of you? How much momentum? The same or more? I say, oh, well, probably more. Come on, free lunch? No way, okay? When one comes in, boom, you get 1 out. 2 in, 2 out. Now, let me ask you a question. How do the balls know? You wonder about things like that, isn't that right? See? The momentum on one side, the momentum on the other side, the same. We say the momentum is conserved. It's just transferred through the system with none being lost and none being gained. So 1, 1, 2, 2, and like that. But I'll tell you what, gang. How would it be if I had 2 of these come down? 2. And 1 come out with twice the speed. If that happened, would the momentum before and after be the same? Think. 2 balls, certain speed. 1 ball pop out with twice the speed. Check the numbers. Can you do that? And when you do that, you find out that there's nothing wrong. But you know what? You could do this for eons and eons, and you never lift up 2 and see 1 come out with twice the speed. No can happen. Why no can happen? Because there's something else that has to be conserved besides momentum. And that something else is what we're going to be talking about next time. It begins with the E, gang. What's it going to be? Energy next time. Yay.